Hello, my name is Fernando Antoneli, and I'm going to talk about homeostasis, singularities, and input-output networks. This is work done with several collaborators. I want to thank them, and also would like to thank the organizers of this conference. The main topic of this talk is the notion of infinitesimal homeostasis. This is a notion that comes from biology, and the prototypical example is given by the temperature regulation in mammals. This is data from this 1946 paper. On the horizontal axis we have the environmental temperature, on the vertical axis we have the body temperature of the animal, and here you have the data points. Nyholt and Reed in 2014 proposed a model for this mechanism of temperature regulation in mammals, and they solving this model and by fitting the solution to this data, they obtain this type of curve that they call chairs or chair curves. This blue curve is obtained from their model, is a kind of piecewise linear function, or almost piecewise linear, and the main characteristic of this is the appearance of this plateau, this flat plateau, followed by these increasing parts. Of course, if you change parameters in the model, you change the shape, but you change the size of the plateau, for instance, but you keep the shape of the curve. Of course, here is not a good fit, but here you have a best fit for this curve to this data set. This is not the only way to model this kind of phenomena. Here we have best least square fit by cubics to the same data of the 1946 paper. You have two mammals here, the brown opossum and it opossum. They have, of course, they provide a different data set, but anyway, you can fit a kind of smooth chair curve to these data sets. And the idea of Golubitsky and Stewart was to provide a framework where this type of curves, smooth chairs, is a natural outcome. So homeostasis is a general phenomenon in biology. Is usually defined as a property of a system in which certain variables, in our case the body temperature, are actively regulated to remain approximately constant despite changes in the external parameters, in our case the ambient temperature, over a certain range. The certain range is the range of the variable, the regulated variable, where the plateau in that input-output function, that blue curve, has this plateau. Homeostasis is also called adaptation in the literature of synthetic biology and control engineering. Some authors formulate its ability to maintain a relatively stable or steady internal state that persists despite changes in the world outside. Usually this use of words stable and steady can cause confusion. Although related to homeostasis, stability is not sufficient for occurrence of homeostasis. And in fact, homeostasis or adaptation refers to persistence of a quantity. The value of some observable does not change on perturbation. Let's say the level of the plateau in the input-output function. whereas stability refers to persistence of a quality. The stability of an equilibrium is not lost under perturbation. So this difference is very important for definition of homeostasis. So it's a quantitative property. So here's an example showing that stability does not imply homeostasis. So in the left we have a diagram of a differential equation with a stable equilibrium. When you vary a parameter, this equilibrium moves in this space, and the trajectory of the equilibrium is given by this blue line. And if we want to look at input-output functions defined by some of these variables, you just have to project this onto the plane generated by the variable and the parameter. So if you look here on the right, you see that these two associated input-output functions, they are increasing functions, and so they are not they do not exhibit homeostasis. So this even though we started with an asymptotically stable equilibrium. So in this paper, Golubinsky and Stewart, Homeostasis, Singularities and Networks, they propose a notion of infinitesimal homeostasis in the context of system of differential equations with an input-output map. And they essentially derived this input-output map from the existence of asymptotically stable equilibrium. So you can use the stability to produce the input-output map, but then the notion of homeostasis is another condition that has to be assumed. So the framework starts with a family of differential equations with some state variable and some parameters, and at some point you have an asymptotically stable equilibrium. At that point, the Jacobian matrix of F is non-singular, so by implicit differentiation and implicit function theorem, you can find a function that parameterizes this equilibria as a function of the parameters. And using this parameterization of the equilibrium points, you can define the input-output map by, let's say, picking up one of these coordinates of one of the state variables as observable. So here I will define, for sake of example, z of I as the last coordinate of the parameterization of the equilibrium points. Now the notion of infinitesimal homeostasis can be defined in terms of the input-output map. So let's assume that our parameter is one-dimensional, a scalar. So we can define several notions of homeostasis. Some of them actually come from the literature of systems biology and control engineering, where they call adaptation. So the first one is the more strict definition, is called perfect homeostasis or perfect adaptation, that occurs when the input-output map is constant over the parameter range. Near perfect adaptation or near perfect homeostasis occurs when the input-output function is approximate constant on a subinterval of the parameter range. And the notion of infinitesimal homeostasis, that is the new one, occurs at a point in the interval of parameter values I naught if the derivative of the input-output function with respect to the parameter evaluated at I naught vanishes. So it vanishes, the derivative vanishes at one point. It's easy to see that these three notions of homeostasis are related, by observing first that the perfect homeostasis is equivalent to the vanishing of the derivative of the input-output map over the whole interval. So the derivative is identically zero for all values of the interval. So obviously this implies infinitesimal homeostasis. On the other hand, it follows from Taylor's theorem that infinitesimal homeostasis implies near perfect homeostasis in a neighborhood of I naught. If you expand the input-output function around a point of infinitesimal homeostasis, it's easy to see that over this neighborhood the input-output function is approximately constant. So these three notions provide different levels of demand on the type of plateau that we expect to see in this input-output function. So in the same paper, Golubitsky and Stewart identified the class of transformation of ODEs that preserve the notion of infinitesimal homeostasis. The transformations act on a vector field by translating the state variables and performing a change of coordinates on the parameters. Here k is a constant vector. This is expected since we want to define an input-output function by some coordinate of the state variable, and if you perform an arbitrary change of coordinate here, you destroy this observable that we fix a priori. This class of transformations induce a class of transformations in the input-output map that are given by a change of coordinates on the domain plus a translation on the range of the input-output function. It turns out that this class of induced transformations on the input-output maps is exactly the class of standard change of coordinates in the elementary catastrophe theory. This is a main observation made by Golubitsky and Stewart here. Now we can define the notion of infinitesimal chairs, namely that it occurs at a point I naught in the range of the external parameter if the first and second derivatives of the input-output map evaluated at the I naught are 0 and the third derivative is not 0. So this is a recognition conditions for a cubic. So from elementary catastrophe theory we know that the universal unfolding of a chair is the cubic function with one additional unfolding parameter a. This unfolding is structurally stable, and you have essentially three types of cubics given here. For when the unfolding parameter is negative, when it is 0, you have the singularity, and when it is positive. The delta plateau is the interval where the chair is approximately constant and is defined by this condition, and this is the size, approximate size of this plateau in terms of delta and the unfolding parameter. Now the idea is that not only we can define homeostasis through chairs, but we expect that this homeostasis is an emergent property of systems. The question is, how does a system evolve towards homeostasis? If you assume very reasonable hypothesis, we can answer this question. So we assume that the system depends on other parameters beside the input parameter I. This is okay. Most the systems are given by differential equations with lots of parameters in that, so this is not a problem. Then we start with an input-output map with a region that has no homeostasis, and no region of homeostasis, so a function that is increasing or decreasing. We vary parameters so that small region of homeostasis appears. So we can produce by small perturbation using the parameters other than I a region of homeostasis. Since this region is small, we can assume that it is generated by a singularity associated with the infinitesimal homeostasis point. So then, under these conditions, we can prove, if we assume that input-output function is scalar, that the only singularities of codimension man that have perturbations with no infinitesimal homeostasis are false and chairs. So these are the only singularities that can evolve towards homeostasis. So the expectation is that homeostasis emerges through chairs, which is a codimension man phenomena. Now the question is how to generate natural examples of this scheme where you have a differential equation with an input-output map that is naturally given, not chosen arbitrarily by picking one coordinate. So this field of biochemical networks is full of these examples, and I will go through some of them. The first one is called feed-forward excitation, where the substrate X activates Y and catabolizes Z. So this is the diagram of the chemical reactions associated with this phenomena. This diagram can be converted into this abstract network that will, where we call this an input-output network, where we have the nodes representing variables and the couplings represented by the connections. One node receives the input, that is the input node, and there is an output node where we observe the value of this variable. So here we have associated, corresponding to this biochemical diagram, the model equations with kinetic functions given by these G functions, and here is the general system of differential equations correspond to this abstract network. Now you can see the parallel here. The function, the equation corresponding to the input node depends on the external parameter, and we have the last equation is the equation associated with the output node that will give us the input-output map. We call the other nodes regulatory nodes. So in this example, it is shown by Reed et al. That infinitesimal homeostasis occurs if and only if this kinetic function satisfies this relation here. Of course, this is evaluated at an equilibrium point of the system, where that is used to define the input-output map. Another example is called substrate inhibition or Haldane homeostasis. It's very similar to the previous one, but if you look at the equations here, this is the model, this is the abstract network. You see that there is no connection between input node and output node. So these are the system of the general system of equation associated with this network. This was also analyzed by Reed et al. It's interesting to know that a lot of enzymes show substrate inhibition in nature. So this is a very important system for biochemistry. So they also derive conditions for this kind of system to exhibit homeostasis. A third example that I want to talk about is this negative feedback loop or Null-Degradation. Here's the same thing. Here's we have this biochemical diagram with the corresponding kinetic equations, and here is the corresponding abstract network and the associated vector fields. The negative feedback loop is this part of the network between the regulatory node and the output node, where you have a closed path. Now the question is, can we provide a general theory to analyze the occurrence of homeostasis in this kind of systems, where now we allow an arbitrary number of nodes between the input node and the output node? We keep only the structure where we have one input node that depends on a scalar parameter, and we have one output node that we use to construct the input-output map. The question is, what are the possible homeostasis that can occur within this type of networks? So we provide a complete answer to this question by developing a general theory of homeostasis in input-output networks, where the homeostasis can be associated with only two classes of mechanisms. We define two general classes of mechanisms that we call structural and appendage, and each one of these classes is characterized by topological properties, which means that you can read these properties from the graph from this general abstract network here. Structural and appendage classes are abstract generation of the usual feed-forward and feedback mechanisms, respectively. So in these three node networks, we have feed-forward structures and feedback structures, and essentially these two types of mechanisms, they are generalized by these two classes of mechanism that we defined in this general theory. In each class above, there are several homeostasis types, with a corresponding network motif that is a subnetwork in the original network up to a topological equivalence, and each of these network motifs give a distinct homeostasis mechanism, according to which is structural or appendage. This theory blends ideas from combinatorial matrix theory and graph theory, adapted to input-output networks to determine properties of equilibrium of differential equations. And the basic ingredient in this blend of ideas is what we call determinant formulas that connects the non-zero summands of age, where age is a matrix that is associated with the homeostasis points, with simple paths from the input node to output node of the networks. So this is reminiscent of the connection between directed graph and its adjacency matrix. So this determinant depth of age is extracted from the input-output function, and it gives you the zeros of the derivative of the input-output, or the critical points of this function. So it's equivalent to study the zeros of this determinant of age function. The bibliography of this theory is presented here. This is the original paper by Golubic Stewart. Here we study this notion of homeostasis in a regulatory system for single cell organisms. Here if multiple inputs, 3 nodes input output, and this is a generalization of Reed et al. To the abstract in 3 node networks. This is a review paper that covers a lot of things here, and the work where we detail all of this general theory is this one, and you can find it on arXiv by using this QR code. Thank you for your attention.